Okay, so now that we know reaction rates and what affects them, how does that correspond to the reaction mechanism? And for that, we'll talk about rate laws. So a rate law is an expression of the reaction rate in terms of concentration of some reagent or intermediate. Of some molecules, whatever. Could be reactant, could be intermediate, sometimes it could be product. So what I mean by that is, if, for example, for our SN2 example that we keep on going back to, I said that the rate for SN2 was going to be equal to K times our electrophile times our nucleophile. So what I mean to say is that our rate of product formation or rate of reagent consumption is going to be directly related to these concentrations. The higher one of these concentrations goes, the faster your reaction goes. So this is the rate law of the SN2 reaction. And then so this is some reaction constant, reaction rate constant. I'll point out that this is a lowercase k. So lowercase k is a rate constant. The uppercase k that we worked with previously is an equilibrium constant, which is thermodynamic, not kinetic. This is only kinetic. And then these are our concentrations. And then the order of the rate law is going to be related to how many things are reacting. So the reaction order is basically the exponents, sum of exponents in this case, the exponent for these two concentrations are both 1. So this is what's called a second order reaction. So this is second order overall because there's two things with both with exponent 1. But you could say also that this is first order in methoxide or first order in butyl iodide because the exponents of both of these are 1. But overall, because we have both reagents reacting and they're involved in our rate law, this is second order overall. And what this tells you, this reaction order tells us about the nature of the transition state for a key elementary step. If you recall that for our transition state for SN2, we have the methoxide approaching from the backside of this electrophile, and then but both the iodide and the methoxide kind of share that partial bond nature. So because of that, this reaction is second order because that transition state has contributions from both of these factors. Yes. And then the final thing is this rate constant. So the rate constant, K, the units depend on your reaction order. Units vary. Because we know that the overall rate has got to be in units of molar per second. And then these units here are both molar. So for a second order reaction, K has got to be in units of 1 over molar seconds, or per molar per second. And that way, this per molar will cancel out one of these molars, and then we'll end up with our final units of molar per second. For a first order reaction, for example, first order, aka SN1 reaction is a first order reaction because only the terbutyl bromide or whatever your electrophile is reacting. Then K is going to be just per second. For a zero order reaction where concentration doesn't matter, talk a little bit about that later. Oops, okay, sorry, that's cut off. I'll go over here, 0 order, then we'll have mole per second. We can have third order, in which case it'll be, mole to the -2 per second. You get the idea. So that's what a rate law is. Cool. So basically, kind of the general scheme is that if you have a reaction, let's say if we have some general reaction, AA plus BB plus C, it goes to CC plus DD. The key point is, though, even though these coefficients of this overall reaction matter for the overall reaction rate, the rate law does not depend on the overall reaction stoichiometry. So keep this in mind. Rate law So the example is for our SN1, our rate law was actually first order, right? So this was this guy. Even though our overall reaction has 2 reagents, goes to, right? This is overall first order because this contribution doesn't matter, right? The bond breaking step, the key elementary step of this reaction was the bond breaking of this carbon bromide bond, and therefore only the concentration of the tributyl bromide matters. So that's why this is first order. So again, this tells us about the nature of the transition state for the key elementary step. So in general, when we want to find the rate law, we have to basically figure out what the order of the reactants or whatever reagents are participating, and that can tell us about the mechanism. So that's how we go from measuring reaction rate to rate law to mechanism. So for this particular general example, we would want to be able to use kinetic measurements of experiments to measure the change in concentration over time. And then we'll want to find our rate. And then that's going to be equal to, if only the reagents are involved, we have to find out K, that's our unknown. And we also need to find out what order these reagents are. So again, it doesn't have to be little a or little b. It doesn't matter if that's not the elementary step. So we need to find the overall coefficients, x and y. Right? So x and y could be 0. If they're both 0, this would be a 0 order reaction. If x equals 1, y equals 0, that's a first order reaction in A. If x and y both equal 2, that's an overall second order reaction, first order in A, first order in B. So this is how, so over the next few lectures, we'll talk about different ways of calculating rate law and then relating that to mechanism.